have to admit that this is an assumption, right? And in many cases, this assumption simply does not hold, because we also know that there are many incidents of kernel level malware infection and malware attack, like the kernel level rootkit, which is considered one of the most malicious, most stealthy, and the most difficult one to detect and to defend against, right? So basically, this approach does have the limitation. If, for example, if the kernel level integrity cannot be guaranteed, then all bets are off. All the tainting mechanism, the tainted log entries are not trusted, right? Fortunately, there have been some parallel works that address the integrity of kernel level mechanism, right? And these are work that preserve the integrity and check the integrity of your operating system and raises an alarm if, for example, if your operating system has been compromised. And also, this information flow-based approach is not very good in detecting covert channels. Meaning that, for example, if I use like some like implicit information to infect or to influence process, let's say two processes communicating via let's say the CPU utilization percentage or the on and off of disk activity. If the two malicious processes agree on some of the signals, right? And let's say that if the disk is on, I mean 1, and if the disk is off, I mean 0. If the communication channel between these two malicious processes is via such information, then this approach cannot detect the influence or the information flow, this covert channel-based flow between them. So there have been some related works that are kind of related to this effort. Basically, first of all, the theoretical underpinning is the operating system level information flow model, more specifically process labeling. And also some of the traditional or current log-based investigation tools include backtracker and forward tracking extension. So basically, these are the systems that use the log entries to reconstruct the steps of malware intrusion. We also have information flow theory applied to other levels. So this is just one level because we focus on the operating system level tainting. And there have also been work on in machine instruction level tainting and language level tainting. So they give you also different level. They review the malware behavior and action at different levels. For example, for the instruction level tainting, they are able to, for example, detect the propagation of a untrusted data, right? With the execution of the instruction sequence. And they use that to actually characterize the vulnerability of the attack. And also, there are language-level tainting mechanisms that will perform the tainting operation within a program, right? And basically, their tainting is at the granularity of variables, objects, data structures, things like that. So they actually happen. These tainting operations happen within the same program. So they will actually zoom in to the specific vulnerable program to find out what is the root cause of this vulnerability, right? So now you realize that these two capabilities, like the tainting operation at these two levels, the operating system level and the language level, kind of complement each other. So for the operating system level tainting, I am able to identify that specific software, right, as the breaking point. But what is the specific nature of the vulnerability? I don't know. Right, so you have to do the language level tainting to uncover, that information. Maybe, for example, it's due to a out of bound statement, or a statement without doing bound checking, things like that. Right. So those root causes can only be identified or uncovered by language level tainting with a finer granularity. So in conclusion, I kind of talked about the taint-based operating system level tainting-based mechanism called process coloring for malware intrusion and contamination tracing, and it is based on a virtualization. It is based on a virtual machine-based implementation, giving you higher tamper resistance for the log entries to perform malware investigation. And it introduced 3 new capabilities. Right, the first one is to use the color to identify the breaking point. The second one is to use the color to partition the log so that when you reconstruct the episode, you only need to use a subset of the entries. The third capability is the one that I mentioned, when I talk about the multiple coloring scenario, where you can use the multiple coloring as a trigger for more timely malware investigation. So you don't have to wait until the user realizes something is wrong, right? The log all of a sudden becomes an active entity, an active guard of your system. The log will tell you something is wrong. So that's enabled by process coloring. If I have time, I would just want to kind of quickly show you some of the client-side investigation that we are just starting to do. So the client-side vulnerability is more difficult because, as I mentioned, the client-side applications do communicate a lot. They are kind of different from the relatively independent nature of server-side software systems. So this one, so basically, let me first show you the incident. So what we do is that we kind of we run a vulnerable web browser. Right? This web browser, is not patched and exhibits 3 different vulnerabilities. The ones that the 3 vulnerabilities, that I show on the left-hand side of the slide. And if this web browser contacts a malicious website, so that website is set up by some malicious party, right? And they want to compromise your web browser. So once you click this link, you got these 22 applications automatically installed on your desktop, without your permission. So I even had to kind of do some sanitization before showing you this, because. So then the challenge is the following: how do you identify this is the problem of your web browser, not like your instant messenger or your email reader or your other software. Right, very similar to the server-side investigation, and then the next step is to reconstruct the whole episode. How these 22 applications get installed without my permission. So you need to reconstruct the story, you need to reconstruct the steps. And as I mentioned, to do that on the client side, you actually have to deal with more noises. You have to deal with many false positive scenario. You have to distinguish the real bad things and the legal interaction between processes, or influence between of the process on individual objects. So I guess I will stop here.
I have time for one quick question.
Yeah.
If the attack of a malware is not targeted at the kernel, but targets immediately the log file, and basically possibly changes the color codes for any way, shape, or form, how would you detect that? I mean, did you take that into consideration at all?
Yes, I do. So I have 2 points to make. The first one is that the log cannot be tampered with by the malware, because the log is stored outside the system, right? If you look at that virtualization-based log collection mechanism. So the log is not even in the virtual machine. The log is outside the virtual machine, and current virtualization technology enables a strict confinement of the virtual machine, meaning that if you are within the VM, you cannot touch things that are outside of VM. My second point is that the tainting mechanism, the coloring operations themselves, are assumed to be trusted. I do assume that the operating system has the integrity of doing the tainting operation, but that assumption does not always hold, unfortunately. So that's the limitation of this approach.
Thank you.
All right. Yes. Hi.
In your implementation, how did you pass the state